everybody, Professor Gentry here. This is going to be lecture 1 for chapter 1 for Introduction to Programming. And it's going to be an overview of computers and logic. So in class, we kind of went through the syllabus just a little bit. We went really into the course schedule. So please take a minute and download the syllabus and look at least the course schedule. There is an assignment after every lecture, and there's labs kind of sporadically throughout. It also is going to tell you how you're going to get your participation, especially if you're asynchronous. It's going to be watching the lectures through the Edpuzzle link, which will be available through the e-learning. So let's get to it. For this very first lecture, we're concentrating more on the Just Enough Programming and Logic and Design book as opposed to the C programming book. Everything that we're learning in here today is going to be applicable regardless of what programming language that you actually use, okay? So this is going to be very generic. We're going to start using C programming in the next lecture, but if you have this book already, it's a very thin book. Go ahead and read chapter 1, just the first section of pages. We'll read the second set of chapter 1 later on in this course. So some of the things we're going to start out this class, again, like I said, language independent. So for example, we're going to be talking about computer logic and planning, and we're not actually going to do any hands-on programming this class. We will, however, be using Flowgorithm, the flowcharting program. So, you know, we'll get to do a little bit of hands-on. That's what your first assignment is going to be, okay? So there are some things we all need to be on the same page with going forward to make sure that we're all speaking the same language, to make sure we're filling in those potholes of knowledge that you may already have, and just to make sure that we are all sort of talking the same thing. So we're going to talk about computer components and their operations just a little bit. So we're going to look at the 7 different steps in the programming process. We're going to go look at each one individually, and we're going to see how it is actually a cycle instead of a start and end process. We're going to learn a little bit about pseudocode and some flowcharts. We're going to look at some flowchart symbols. And finally, we're going to discuss the evolution of various different programming techniques and what it means when we say like a higher level language versus a lower level language. So first, we're going to talk a little bit about the understanding the computer components and how they operate. So 2 main things to know about a computer is that you have something called hardware and you have something called software. Hardware on a computer system are those things that you can touch, and they are the physical devices for a computer. So it could be a peripheral like a keyboard or a mouse or a monitor, or the actual tower with all of the components like the CPU and memory built inside. Software, on the other side, is the computer's instructions. So that's how your computer knows what to do. It's how your computer knows what to put on the screen and how to put it on the screen. So programs, we're going to call it the set of instructions that is written by programmers that the computer understands, and the act of programming is writing those instructions. So programming here is your verb, and the program is your noun. So these are just a few definitions. A lot of you are probably already familiar with a lot of these, but again, we're making sure we're all on the same page. And, you know, we're going to be explicit with our definitions so that everybody has the same understanding. So now that we have that out of the way, let's look at software portion just a little bit closer, because that's really where your computer programming is going to live. Within software, there are 2 main types: application software and system software. So in application software, this is going to be software that is dedicated to doing a specific single task. This is something like word processing, a spreadsheet, payroll, inventory, things like that. On the other hand, system software is going to be the programs that your hardware is going to use in order to know what to do. So it helps you manage your computer. The largest, most common, part of system software is an operating system or a device driver. So when we're talking about things like Windows, Linux or Unix, Mac OS, or a device-specific driver, that is going to be your system software. Now, in this class, we're actually staying primarily in the application software world, but all of the concepts that we're kind of learning are actually, you can apply to either one. So between your hardware and your software, your computer as a whole does three basic functions. It takes input, it does some sort of processing, and it does an output. So your input could be anything from a hardware device, such as a peripheral, like a keyboard or a mouse, a scanner, your voice, things like that. It can also mean data or facts from a database, things that you're loading through a different method of an input device. It could be data gathered off of the internet. Okay, all of that's considered input. Processing is actually doing something with that input. So it can be something as simple as organizing the input, checking it for accuracy, or doing actual mathematical and arithmetic operations on them. You know, processing is not just necessarily that arithmetic portion, which some people think it is. So the hardware that is going to do the processing is actually called the central processing unit, or the CPU. I'm sure you've probably heard of that term before. Finally, there is no reason to be doing something unless you need some kind of result or some kind of output. So output is sending that information to somewhere to either be viewed, to be read, or to be archived. So when we're looking at output, we can look at monitors and printers. We can look at speakers, okay? Any way that is going to take what it processed and give it back to the user. We can store output on disks, flash media for later retrieval. We could have it be volatile and just disappear. And we'll get into some of those definitions here in a minute. No matter which programming language that you want to concentrate in, you're gonna know these universal terms. So the first term is programming language. So these are gonna be your computer instructions written within a general set of rules, okay? Those rules are gonna differ between languages, and that's really, you know, where you're gonna, and we're gonna get a little bit more into some of the differences between these languages. When you write a program, it is said that you are coding a program. I'm skipping a little bit to the right on the slide. So it is called that you are coding a program. When the computer, when you write these instructions for your computer, it is saying that you are writing either program code or source code, okay? Eventually, it is going to be translated or compiled into an operating code or a machine code, and we're going to see that in a minute. Last but not least, the word syntax. Syntax is going to be the rules that surround what you have to do in that programming language. What do the words mean? Do I need quotes? Do I need semicolons? Do I need colons? Do I need spaces, tabs, carriage returns? The syntax is basically pretty equal to the grammar in the English language, okay? It's going to be that set of rules to explain to you how to use that computer language. But computers don't actually understand words of English. So how does that communication happen? So each programming language uses something called either a compiler or a translator to change that program code or source code into an object code. The object code is then what the machine can understand. Sometimes we call it machine language. Now, a computer is a set of electronics. So in essence, there's only two things it can do. It can either be on or off, or a 0 or a 1, okay? The representation of those zeros and ones of electricity is written down as something called binary form. You may have heard the word binary and just know it's, you know, zeros and ones, but that's really what it is. It means it is whether there is electricity on or off. Now, we have to somehow get from that source code that the programmer creates into that object code. And this is where they have some kind of translation software. So we have something called a compiler, and then we have something called an interpreter. And yes, compilers and interpreters are two different things. So here's a good graphical representation of the difference between a compiler and a translator. So for anyone that has programmed before, C, C++, They actually use a compiler, whereas Python and JavaScript, they use interpreters. So a compiler is going to go through the entire source code at one time, whereas an interpreter is actually going to run line by line. So typically compiled programs are faster than the interpreted versions of them, but debugging interpreted programs is a whole lot easier than if it were being compiled. They each have their advantages and their disadvantages, so there's not really one that's, say, better than the other. So when a program instructions are carried out, we say that the program is either run or that we have executed the program. So let's look at a few different things that can go wrong when we're executing. So we have a word called syntax, right? We talked about it before, and that's those rules of the language that we're using. So a program that is free of syntax errors can be compiled or interpreted, and it may run, but it may not actually give you the answer that you think, or it may not be doing what you think, okay? So syntax errors are actually errors that prohibit the compiler or translator to run. They're gonna stop. You have to fix those errors before you can finish running or executing that program. Now, if there is an error once it's compiled and it's more during the runtime, we call that more of a logic error. And the logic errors might be instructions out of sequence, missing instructions, instructions not part of the procedure. You may have added 3 instead of subtracted. These are definitely errors that are harder and more difficult to find than your syntax. Your syntax errors, your compiler or your interpreter is going to tell you that it's a syntax error. They most of the time tell you where the error is, and it's a little bit easier to fix. These logic errors, they're a little bit more buried. So unless you run through it during testing and you have the expected outcome, you may not find those logic errors. So anything that's not making sense within the context, that's called a semantic error. And again, those logical errors, much harder to find. So computer's memory, in order for your computer program to actually run, it must first be loaded into the computer's memory. That's how the computer is going to take those instructions and know what to do with them. Memory is that internal storage of a computer just in general. But when we speak of main memory or random access memory, or otherwise known as RAM, then we're talking about a very specific portion of that memory. So internal memory is temporary, or we use the word volatile. So that basically means that anything that is being held within that memory is completely gone as soon as that machine loses power, as soon as it or restarts. So at the very beginning, programmers would refer to memory locations by their addresses. And after a while, the binary became quite a bit, and so hexadecimals form. Hexadecimal is just a grouping of binary in which instead of going just zeros and ones, we then go from 0 to up through some of the alphabet letters. So we'll be looking at that later on. But just for this, know that at the beginning, we were able to actually access memory using an address the same way you would access a house, having a street address. So the programmer's job can be broken down into 7 basic steps. This is called the program development cycle. And it's just that, it's a cycle of repetition. So as you can see, there's no start and there's no end. Typically, we do start at the top of the circle, though, if it is a brand new project. So the very first thing we have to do is understand the problem. Then we're going to plan the logic. Finally, we're going to write the code, then translate the code, test the program, put the program into production, and then maintain. Once you maintain, you can then go up to the top and either start the loop again for errors and bugs, or even for adding additional functionality into your program. Now, one thing I do want to point out is in much larger organizations, these boxes may be different people. They may be different departments. They're not all going to be one person. In smaller companies, sometimes it's all the same person. So in larger companies, you may have someone who is only writing code and they're just a coder, whereas you may have someone else that is actually planning the logic out of what the programs is going to look like. So first, step one, understanding the problem. So professional computer programmers write programs typically to satisfy the needs of other people. Okay, 9 times out of 10, you're not writing it for yourself, you're writing it for someone else. So what you really need to do is you need to really understand the problem at hand. Okay, and understanding what your user wants can sometimes be the most difficult part of all of this. Sometimes, unfortunately, your user doesn't even know what your user wants. So anytime that you are in this understanding of the problem phase, you know, your description from your user may be extremely vague, or again, they don't know what they want. Users also frequently change their minds. They might see a sample output and want it to do something else. And a good computer programmer is oftentimes part counselor, part detective. You want to put some options out there for your user. You're trying to get them to narrow down their choices into a single decision. Okay, and sometimes, like it says, your user is not going to know really what they want. Planning the logic, the next step, is the heart of the programming process. This is really where the programmers are set apart from the coders, okay? During this phase, the programmer is going to determine how the computer needs to think, what steps it needs to go through, and in what order those steps need to be in. And we call this sequence of steps an algorithm. So you're going to use the word algorithm throughout your career. It's a very, very normal term to use. But while you're doing planning, there are 2 most common tools that are used. One is called a flowchart, and the other one is pseudocode. So just like the picture here, the flowchart is those graphical representations with those boxes and things, and we're going to look at what all those boxes mean here in a minute. And pseudocode is an English word representation of the steps line by line. So again, it's not going to be any programming language specific. You're just laying out the roadmap of where you want your program to go and what do you want it to do. Again, we're going to look at this a little bit closer in a few extra slides. Planning the logic. So, you know, we're going to find, you need to know what to do and what order to do it in. So you need that sequential set of steps. So this includes thinking carefully about all the possible data values that you might encounter and how you want to deal with each scenario. So for example, if you want to have an input of an age and someone types in the word BLUE, what do you want to do? I know you're expecting a number, but what's going to happen if your user types in a word instead? If you ask for an age and someone types in the word TEN instead of a 1 and a 0, what's it going to do? This is really where the planning of the logic is going to come in handy. You want to find all those outliers. We don't just want to know what your majority of your data is going to an input it looks like. We want to find those outliers and how we deal with those. The process of taking this walkthrough of the basic logic on paper is called a desk check. Now we move into coding of the program. Now there are over 400 programming languages out there and floating around the world at all different levels. So how do you know which one to pick? So only after you have figured out the logic can you actually make a determination as to which programming language is best for this project. So your programmer is going to choose a language in particular because of built-in capabilities. Some are more efficient at doing some things than others, or maybe it has to handle a certain type of operation or deal with an interface with a specific type of software. But there are many different reasons to choose a programming language, and sometimes, unfortunately, we're not allowed to choose. They're kind of chosen for us. Now, using the software to translate the program into that object code or that machine language. So Again, even though there are over 400 programming languages, your computer only understands one, machine language. That's it. So what you need is you need that translator program. And when I say translator program, I'm going to refer to compiler or interpreter, kind of using them in the same breath, even though we know they're different. And what it's going to do is it is going to turn a higher level language into a lower level language. Now, a higher level language is closer to the English spoken language, and the lower level language, actually the lowest level language, is machine language, or that binary of ones and zeros. So your program has to be free of those syntax errors before you can do it. And then you have a specific translation program that is associated with whatever language you use to program. It's going to go through your program and translate it into those ones and zeros so that your computer can then execute. Now, here's a good graphic of some of the programming language levels. Again, more towards the bottom, lower level, more towards the top, higher level. So at the bottom, you've got machine language and assembly language, and going up, you've got C, C++, Java, Pascal. Actually, even a higher level language is SQL or SQL, and you're getting more and more towards actually just spoken English and less into sort of those nuances of talking to a machine. Testing the program. So once it's free of errors, you know, it's not necessarily free of those logical errors. Remember, syntax errors, logical errors, completely different. So you have to be able to select a test data set. That's an art in itself sometimes, just figuring out what to use for test. And, you know, many of these programs are not going to realize that it has an error until it encounters some of those outliers. So again, going back to my example from before, if you are expecting an age input into a text box and someone types in a word, that is not a very common thing to happen. But that's that unusual circumstance that's going to occur, and that's when you're going to know whether your software is actually working or not. After testing, we're going to put it into production. So once it's adequately tested, it's ready to use. So it may be as simple as just hitting the run button and running that program once. Yay, we're done, and we've put it into production. Most of the times, though, out in industry, it's not that easy. Sometimes it may take months. It's going to be implemented on many different computers, maybe within an organization. And it's not always just quick and easy. So sometimes the switch over to the new program can be gradual, sometimes, or they can just be all at once and all of the new features are available. There are different types of putting these programs into production, and usually that's determined ahead of time so that it can help the programmer understand how to program. Finally, the last step in the cycle is to maintain the program. Sometimes it's a step that's often forgot about or not done, but after you put it into production, there may be errors that are found. There might be changes that need to be done. So maintenance is actually the whole process of updating and correcting these issues. So one thing I do want to point out here is that maintaining source code is not as easy as it sounds. We always appreciate the efforts of the programmers before us, especially when it comes to commenting and doing your programming in a very clear, concise way and documenting what you did so that others can pick up the maintenance phase. Remember, I said in that cycle, sometimes it's different people, sometimes it's a whole different department, sometimes it can be a whole different business. I'll be honest, when I was doing a lot of coding, there were some times when I would look at my own code 2 months from when I wrote it and not understand what I did. So how in the world could I possibly expect anyone else to pick up my code and understand it if I couldn't even do it myself? So one thing to look at is that this is a cycle, okay? So any changes to the existing program repeats that development cycle over and over again. So if you have a change or an update, you're gonna go back to step one and understand the change. Plan, code, translate, test, put it into production, and then maintain, okay? That's how we get that cyclical kind of shape starting to form. Now, let's take a quick look into flowcharts and pseudocode a little bit closer to help us with our assignment. So pseudocode is going to be an English-like representation of the logical steps within a program. So there's an example here. There's usually a start and a stop. There's typically an indent between those so that we can see things that line up. And it is something as simple as saying input a number, output the answer, and in the middle, compute this, okay? We are not getting into the nitty-gritty of the programming language. This is very generic. I can read this and understand what you want to do. Now, the whole purpose of this is basically for programmers and non-programmers to be on the same page. Typically, if you're writing a flowchart or pseudocode, you're actually going to be bringing this to a set of non-technical people, and you want them to understand as fully as possible what your program is planning on doing. A flowchart, on the other hand, is a graphical representation of the same thing as pseudocode, except it's in pretty pictures instead of words. So when creating a flowchart, it's a lot of geometric shapes around different statements and variables. Each one of these shapes actually has a meaning, okay? So a parallelogram, which looks like this, is going to be an input symbol, and it's going to indicate that you're going to wait on user input or it needs an input operation. Next, we have the rectangle, and that is going to be some sort of process. You're going to do something. It can, remember when we said do something, it can be arithmetic, it can be organization, it can be sorting, things like that. Again, now the output, we see the parallelogram again, output. So the parallelogram in general is considered an I/O symbol or input-output symbol. I/O means input-output, and that's going to indicate whether it's an input or an output. Typically within that parallelogram, you'll say whether it's input or output. Now, to show the correct sequence of these geometric shapes, we're going to use things called flow lines, okay? The flow line is nothing more than an arrow. So a flowchart is a one-way street, and we follow the arrows. So in this, we've got a process, and it goes down following the arrow into an input-output or an I/O, okay? When you start or complete a flowchart, there is a special symbol you can see here down at the bottom called a terminal symbol. Typically, they have the words start or end or main in them, and that's what's going to start or finish your program. These terminal symbols, to me, it looks like a medicine pill. Not really sure what the shape is called, but again, remember, it's called a terminal symbol. So let's take a look at an example. We're going to use our pseudocode from before, and we're going to add a flowchart to it. So here we go. We have the same pseudocode that we had a couple slides ago, and we have input original number, calculate something, output calculated answer, and then stop. If I take that and I put it into the flowchart, the start and the stop, that's those terminal symbols or the medicine pill looking thing at the top and bottom, and we put the words start and stop. We can take the next line of pseudocode where it says input original number. Well, I know input is a parallelogram, so that's the shape I'm going to use. And within that parallelogram, I'm going to type the words input, and then I'm going to put original number. I know the next line is a compute, which is a process, so it's going to be a square. And I put in that square compute, and I put into words the equation, or I can just type the equation out if I know it, kind of like you would see it in a math book. So for this, you could actually put calculated answer, an equal sign, original number, *2 to be times 2. The next statement of pseudocode we have is output, calculated answer. So again, parallelogram, input output symbol. In it, we write output and what we want to output. That's really all there is to making a flowchart. So your assignment 1, is actually going to be making a flowchart from some directions, a bulleted set of directions. So we're going to kind of going through this translation and seeing what it says and what symbol it means. People have been programming and writing modern computer programs since the 40s, which isn't that long ago, even though it kind of seems like it is. The oldest programming languages required programs to work with those memory addresses and to memorize a whole bunch of awkward codes associated with that binary machine language. Now, newer programming language languages look much more like written English or a natural language, and they have become much easier for programmers to use. You know, if you want to print something, you use the word print instead of having to know what code is associated to the print statement in machine language. Now, modern programs use something called modularity, and this is the ability to make smaller chunks out of larger programs. So this course only is going to go through the basics of procedural programming. We'll get into object-oriented programming in the advanced class later on. But I want you to kind of understand what these terms mean. So techniques used to develop programs, we have this procedural programming in which we're going to focus on the procedures that programmers use to create anything they want to do. And it's going to be breaking down those processes into much smaller, more manageable tasks. What we're going to go and learn later on in another course is that object-oriented programming. Now, object-oriented programming is actually going to create something called an object, and an object is going to contain the data and the behaviors or procedures associated with that data. So if I have an object called a car, it's going to know how to drive, and it's going to know what bumper means. So things like that. It's a little bit fancy, it's kind of fun, but in this course for the 7 weeks, we're only going to stick to that procedural programming for now. So in summary, we talked about hardware and software being the two major components. We talked about those 7 major steps that the programmer's job can be broken into and how it is basically a cycle. We talked about pseudocode and flowcharts and 2 major techniques to use to develop programming, being that procedural programming and object-oriented programming. Now, what I want to do real quick is I'm going to switch over to my Flowgorithm, which is in the syllabus as the flowcharting program, and I'm just going to point out a few things before we end this lecture. So, when I first open up Flowgorithm, this is what I see. So, they start out by giving you the terminal graphics already there. They start with something called main and it goes to end instead of using the word start. Now, in order to add a new geometric shape, all you have to do is click on that flow line. Once you click on that flow line, here's all your input output statements. Now, in particular, Flowgorithm does differentiate between input and output, even though they are both parallelograms. You can see there's a slightly different color. The other thing that we have is they, instead of calling it a process, they call it a sign. It means the same thing. So for your assignment, what you're going to have to do is go through and add all of the different things that you want to put in here. And I'm just going to put the 3 that we talked about before in the flowchart and the pseudocode. If you want to type in within the box, you double click in the box and you can type in the variable name. In the assign, you double click and you can put an expression in mathematical terms. So you can say x equals 4, something like that, and it'll show up in the box. Now, the other thing is that you do need to save this file, and I'm going to save it as junk, and I apologize, don't save yours as junk. Do as I say, not as I do. But in order to submit this as your assignment, what you're going to need to do is you're going to have to do a print, hit OK, and print to a PDF. Now, we have to do this because the filtering system on our e-learning is not going to like the file extension of these Flowgorithm files. So print it to a PDF, save it as your last name assignment1.pdf, and that's what you can submit for assignment 1. So hopefully you learned a little bit in this lecture, and now can't wait to get into that C programming in the next lecture. So see you next time.